All right, hello everybody. Welcome back to Math for Machine Learning. Let's see. So this is the last lecture before the exam. The exam is in class next lecture, which is Monday. We'll post more details on Piazza ahead of the exam, but basically you should plan on an 80-minute exam in class. And we will we'll provide extra time at the end to, for any uploading tasks that you might need. We haven't decided exactly how much to provide. But you should plan that the bulk of the exam is in class. I'm going to, if there's time at the end of the class today, I'm going to use it to answer questions that people might have about topics for the finals. So please start thinking about those. And if we get through the lecture notes ahead of the end of the class, I'll take questions about that. All right, so we're going to finish up on differentials today. So last time around we were just starting on the second differential. So if you remember, first differential is a function that takes two arguments, a point that you make a Taylor series at, and the increment for the Taylor series. And those are both in some vector space U, which is the same vector space as the argument to F. And then it gives an output in V, which is the output vector space of F, which is the increment in F that you expect with that increment in X, according to the Taylor series. So a typical form would be A of X dx, where A is a matrix for each fixed X, and dx is a vector. The second differential is going to be, instead of a linear function of X, it'll be a quadratic function of X, of dx. And so let's go through that. We went through that derivation at the end of class on Monday, but let's go through it again. So we start from f of x and we take its differential. That gives us df, which has x and dx as arguments. And now we're going to make a new function g by fixing the dx argument of df. So g of x is df at x, and then u is going to be a fixed vector u. And so then we take the differential again. So we take the differential of g, dg of x. So that's a function dg of x and dx. And now we fill in u for the dx argument of dg. And so we have d squared f at x in the direction u is defined to be dg at x in that direction u. So we gave the same argument u for both instances of the differential in x. And that's what makes it a quadratic function of that argument. And so an example of that would be to get the gradient and Hessian of a real valued function. So if our input vector space is Rn, our output vector space is R. df is going to be of the form A of x dx, where A of x is a 1 by n row vector, the gradient at each point x. And d squared is going to be of the form dx transpose big A of x dx. This is a quadratic function of dx, and big A is called the Hessian matrix, and again it depends on which point x you evaluated at. And then the short form of those, what you would usually see in a paper, is df is A of x dx, and d squared f is dx transpose A of x dx. All right, so why would you want a second differential? Well, you could use it to make a second order Taylor expansion. So here's an example. You have a function f which has it has one real input and three real outputs, and it looks like this. So this is a helix. The plot's down here, right? So it's the blue curve, which is a helix. Then df, we take the first differential. You can do it by the chain rule, and it looks like this. And then d squared f, we take the derivative again. Again, the chain rule, this should be f double prime of t dt squared. There's a missing squared here, I just noticed. And so the second order Taylor expansion you can make out of these two things. The change in f is the first differential plus the second differential, right? So we're making it one term more accurate. Sorry, plus half the second differential. And so the rule for the Taylor series says, in general, that the coefficient of the kth differential is 1 over k factorial. And so this, again, this is shorthand for the longer version, that f hat of t is f of t hat plus f prime of t hat times the increment in t plus half f double prime of t hat times the increment in t squared. And so if we plot on the same graph, f is the blue curve, the helix. At this point here, the Taylor expansion is the red line. That's the velocity that a point would, a point would, if you were moving it around the curve and let it go, it would fly off in that direction. And then the best quadratic approximation is that purple curve. All right. So that is a second order Taylor expansion. Now, just like the first differential, in addition to just knowing the meaning of what a differential is, it helps to be able to compute it. And fortunately, there's almost no new rules to use. You calculate it just like you calculate the first differential, with one exception. The one new bit of information is that when you're taking the second differential, there'll be copies of dx in the expression that came from taking the first differential, and we pretend that those are constant for the purpose of taking the second. And so, for example, one of our examples last time around was to get the normal equations by differentiating squared error, and we got this answer. And if we differentiate again, we take the differential of ax minus b transpose a dx. And because we can treat a and dx both as constant, we push the differential into this term, right? And then because transpose is linear, we push it in one step farther, and b is a constant, so it vanishes, and the differential of ax is a dx. So we get dx transpose a dx. And maybe that's not surprising to anybody who's differentiated a quadratic expression of a vector argument before. This is a fairly standard looking form. But you can see that even though we wrote out in a lot of detail every step, it was a very short derivation, and the representation is nice and compact. With multiple variables, everything works the way you might expect. Take the differential again, to take the second differential, you just treat all previous instances of differentials as constant. So if you have f of xy is cos x times sine y, the first differential we can get by the product rule, right? So the derivative of the first times the second, right, and the derivative of the first is minus sine x dx, and the second is sine y, and then the first times the derivative of the second, and the derivative of the second is cos y dy. So that's an instance of the product rule. And then if we want to take the second differential, we do it again. And since this term is a product, we expand it using the product rule. And since this term is a product, we expand it using the product rule. And the first line comes from this first term, and the second line here comes from this second term. And so you can see you get dx squared, dy squared, and then two terms that involve dx, dy. And unsurprisingly, maybe we can keep going, take the third, the fourth, whatever differential we want. For the purposes of this class, and probably most of the future machine learning classes, it's unlikely that you'll need to go beyond the second, but it's always nice to know that you can. And you'll get a quadratic function for the second, a linear for the first, a cubic function for the third differential, and a quartic function for the fourth differential when you think of it as a function of the dx argument. All right, so So that's differentials. Please ask questions as somebody it looks like already has. Um, so how often do you come across matrix differentials in practice? That depends what sort of thing you like to do for entertainment. If, like me, you read machine learning papers for entertainment, you come across them fairly often because they are by far the most convenient way to take the derivative of an expression that involves matrix and vector and tensor arguments. In machine learning in general, it's important to, like, you'll often have very complicated sets of parameters. It's actually important enough that there are starting to be automatic tools. So for example, if you look in TensorFlow, which is one of the popular toolkits for deep learning, there are tools for automatic differentiation inside TensorFlow. And so you might say, oh, well, TensorFlow will do it for me. I don't have to learn this stuff. But in fact, so A, it helps to know what's going on inside TensorFlow because nothing ever works right the first time. And in order to fix the bug and get it to work right, it helps to be able to understand what's supposed to be happening. And second, I've also often run across situations where you get to some expression that TensorFlow can't automatically differentiate. And third, if you set up the expression wrong, the derivative might be much easier or much harder to calculate. Like computationally, it might turn into a million by million by million by million tensor, in which case you're sunk. Or it might turn into a 10 by 10 by 10 by 10 tensor, in which case you're pretty happy, right? So basically for vanilla cases, yeah, you can let TensorFlow or whatever toolkit do it for you. But a lot of times, like fixing what goes wrong, like understanding why some expression isn't as efficient as you want it to, or going beyond what the automatic tool can do for you, it's really convenient to be able to do this. Why no more than second order differential? Just because. Let's see. So if you take the second differential, you get a quadratic approximation to a function, and that's enough to allow you to apply Newton's method for optimization. If you don't know Newton's method, don't worry about it. We're actually going to mention it in the second mini. And then beyond that, there aren't a lot of computational reasons to need higher differentials. Now, there are, I actually went to a talk the other day where somebody was looking at, 12th order polynomial approximations and had a valid reason for doing so. It wasn't just out of, a fit of orneriness that they decided to do this. And so it's not 100%. It's just that by far, the linear Taylor approximation is the most common because it's really useful to be able to make a linear approximation to stuff. The quadratic Taylor approximation is a little bit less common but still useful because then, like, you can, to minimize a quadratic, you can solve a set of linear equations. And then once you get farther, it just becomes harder the derivatives become more unwieldy and harder to make use of. All right. So continue to ask questions. I can always go back and answer them. But now let's move to our last set of lecture notes. Now we're going to take a look at statistical inference. And so throughout the course of the semester, of the mini so far, we've done a few different examples of machine learning methods. The perceptron algorithm, the Fisher discriminant, and then most recently least squares. We haven't said how that can be used as a machine learning method, but it's the basis for linear regression, which is a very common machine learning method. These are all, they're useful, but they're fairly specific instances. Now we're going to get to a general principle, which lets us derive a lot of different machine learning algorithms. And so you'd use this principle a bunch of times for different algorithms throughout 601 or 701. So let's start with a very simple situation. Suppose we flip a coin 20 times and it comes up head 15 times. Is the coin fair, right? How would you go about answering that question? So this is the question of statistical inference. And the statistical inference basically just means if you have a question that involves randomness, how do you evaluate the evidence in favor or against various conclusions? The way we are going to solve this question is through a model with parameters. So a model is a guess that we make about the way the world works. A parameter is, some number that goes into the model that we don't know and we want to find out. So for example, our coin flip, we could say that there's one parameter, the probability p that it comes up heads. For a single coin flip, that's about the only model you can make. And our parameter, of course, is this probability p. And in general, our job is to figure out as much as we can about the parameters from data. And so we might want to, from a coin flip, figure out what we can understand about the probability p. Presumably, for example, if the coin comes up heads, we increase our belief in p a little bit. If it comes up tails, we decrease our belief in p a little bit. All right, so let's go a little bit more complicated than a single coin flip. Let's say we want to model a whole bunch of coin flips in a row. Now we have a few more choices, right? So we might say that every coin flip has the same probability of coming up heads. Maybe that's the simplest model. But we could say more complicated models, that the first 10 flips come from one coin, and then the person switches the coin and pockets the other one without us noticing, and it changes the probability for the next 10 flips. Or you might have what I would call the Las Vegas model, which is every time the coin comes up heads, it increases the probability of future heads, right? Like that's the idea of having a hot slot machine. So there's a lot of different possible examples, but by far the most common model that we're going to use is the first one that I described, which is the IID, or independent identically distributed model, which says every flip has the same probability and the flips are independent. They don't influence one another. All right. So all of our probability so far in this class has been on discrete random variables. And there's a very good reason for that. There's a lot of sort of weird things that happen when you try to do probability on continuous random variables. So what we're going to do is, rather than go into continuous probability, we're going to just pretend that our parameters are discrete. So instead of learning a real valued probability between 0 and 1, we're going to say it's represented by a 32-bit floating point number, or a 32-bit fixed point number, or just that we, discretize the interval from 0 to 1 into 1,000 different possible probabilities at intervals of 0.001, and I guess that would give you 1,001 of them. Anyway, discretize it and work with only those discrete choices. And so mostly that doesn't have any effect on all of our inference questions. But I wanted to point out a couple of things that are important. One is that our choice of discretization matters, right? So I talked about two different discretizations for real numbers. One is to use a C float data type, which is 32 bits. There are 2 to the 32 possibilities, except that a few of them are not used for actual numbers. So that's one way. The other way is to evenly break up the interval from 0 to 1, right? Or the interval from the largest possible number that we're going to consider to the smallest possible number we're going to consider. And these two are very different. So if you know about the floating point representation, it actually gives you much more resolution near 0. Tiny floating point numbers are better sampled so that you can get sort of relative accuracy even close to 0. So these two discretizations have different properties. The one with, and the easiest way to see that is to imagine the uniform distribution over either one of those two discretizations. Right, if it's an even discretization, then the interval between 1 and 2 has exactly the same probability as the interval between 0 and 1 or the interval between 2 and 3. If it's an uneven discretization like the floats, the interval from 0 to 1 will actually have much more probability than the interval from 1 to 2, which will have more than the interval from 2 to 3. So the choice of discretization matters. Another way that it could matter, right, would be suppose we decide, say we have a positive parameter and we have the choice of discretizing the parameter theta itself or the log of that parameter, right? That will give us a very different idea of what a uniform distribution means. And I want to point out two things about this annoying problem. One is that you might think that it's an artifact of the fact that we decided to discretize, and it's not. The problem actually exists. It existed from the beginning with a continuous parameter, and it actually would have been much harder to deal with if we left the parameters continuous. And if you want some additional evidence about how annoying it is to deal with for that case, you can click the link in the notes to get to the Wikipedia page on the Borel-Kolmogorov paradox, which I think we mentioned earlier in the mini. The other is that a lot of times I describe a problem and then I tell you what the answer to that problem is. Sadly, I don't know the answer, and as far as I know, there is no good answer to this problem. You just have to pick a discretization that makes sense, and you'll potentially get different answers with different discretizations. And you know, if you get a different answer than somebody else, then you just have to argue with them about who had the better discretization. We'll say a little bit more about that below. All right. Can I explain the Bernoulli distribution? Yes. The Bernoulli distribution is basically the simplest possible distribution. It's the one that you would use automatically to model a flip of a biased coin. There are two possible outcomes, true and false, heads and tails, 0 and 1, and it's got one parameter, which is the probability of one of the outcomes. So, so that's the Bernoulli distribution, and that's really, it's very simple. That's all it is. We'll get to more complicated distributions later. All right, so we have our model, we have our parameters, and we're going to start out building a prior distribution that says what information we know about the parameters before coming in. So if we don't know much, we might pick a uniform distribution. If we know that they're more likely to be smaller, we might pick a distribution that has more weight on smaller values of the parameters. And then we see data, right? These are our coin flips. And hopefully that tells us something about the parameters. And so we update our prior to become a posterior, right? So we have our prior is the joint distribution of all of the parameters, before seeing the data or marginalizing out the data. The posterior is the conditional distribution of our parameters given the data, right? And then, we don't have to do this just once, right? Like after we are done reasoning about the data that we've seen, somebody might come and deliver us a new USB stick full of new data, and we might update our parameters again or update our distribution. So that means that our new prior becomes our old posterior, and then our new posterior we condition on data prime, the new data, and we get the P of parameters given data and data prime, right? And so this process should look familiar because it's exactly a Bayes filter, right? If we have a hidden state which is equal to our parameter vector, and we have a distribution that we keep updating after we see observations, that's exactly what a Bayes filter is, and it's exactly what our task is here when we're doing statistical inference in a model. And this particular use of a Bayes filter is ubiquitous in machine learning because all the time it happens that we start out with parameters and we get a stream of data coming in, and we just keep wanting to update our belief about the parameters given all of the data we've seen so far. So So there's a question that says to explain more about the uses of Taylor series. So the simplest way to say it is that suppose we have some complicated function and we're looking at that function in the neighborhood of some point, and there's nothing we can do with it because it's too complicated for us to reason about. So what we can do then is we replace the complicated function by a simpler one, a linear function or a quadratic function, and we reason about that simpler function. And those conclusions that we draw are going to be valid locally around the neighborhood where we made the Taylor approximation. So an example of this would be optimization. If you make if you have some complicated function you want to minimize, and you make a quadratic approximation to that function at a given point, right? Let's say we keep, the current value of our parameters, and we're trying to find a better value of our parameters. To minimize, we don't know how to minimize the complicated function, so we make a quadratic approximation to it, and we minimize that quadratic. And hopefully, as long as the quadratic is a good enough approximation to our function, we actually improve the value of our function by minimizing that quadratic. That minimization algorithm is called Newton's method. I mentioned it just a few minutes ago, and we're going to talk about it in the second mini. An even simpler one is to say, is gradient descent, right? So we have some complicated function, we make a linear approximation to that complicated function at our current value of the parameters, and we take a step downhill on that linear approximation, and hopefully that's also a step downhill on the original function. Yeah, so hopefully that answers the question. Prior and posterior, what impact does the initial prior make, and does it matter? Yes, the prior always matters. If you and I have different priors and see the same data, we'll have a different posterior. Hopefully our posteriors will be closer together than the priors were, but even that is not always true. So I guess the way to say it is that the prior affects the assumptions that we have going into a discussion, and those always are going to influence the conclusion that we draw from the discussion, particularly in the case where observations are noisy and there's not complete information in them. I might comment on how the importance of priors is shown by political discussion, but I don't want to get into differences between my prior and other people's priors in political matters. But suffice it to say that if you come into a discussion with differing assumptions, you might leave it with differing conclusions. All right, so all right, so let's just review what the Bayes filter looks like in this context, right? So we want to compute the probability of our parameters given our data, and Bayes' rule says that's equal to the probability of the data given the parameters times the probability of the parameters divided by the probability of the data. And just to remind everybody, this was something that came up with a bunch of questions about one of the past assignments. When we use the conditional probability notation, we're going to pick a state of knowledge, maybe a time point, and our state of knowledge at that time point. And we're going to say that at that time point, that's where we're going to use the notation P of X, right, without any conditioning. And then as we get more knowledge, or if we imagine getting more knowledge, that's when we use the conditional, right? So in this case, P of parameters, the time point is before we receive the data, right? So this is the distribution over our parameters before we see any data. This is the distribution of our data that we believe before we see any data. Then this is the distribution of data supposing we knew a value of parameters, and this is the distribution of parameters supposing we knew a value of data. Right? All right, so the prior is P of parameters, and the posterior is P of parameters given data, right? So this is one of the inputs, and this is the desired output. That leaves two more terms here on the right-hand side. So P of data given parameters is called the observation likelihood, or the data likelihood. It basically tells us how happy is any given set of parameters in explaining our data. So for example, if we see 20 heads in a row, a probability of 0.9 for heads is going to be much happier explaining that than a probability of 0.1 for heads. And so qualitatively, what Bayes' rule says here is exactly that parameters that explain the data better will have higher posterior weight. All right, and then that last new term, P of data, is potentially a problem because we typically don't have a way to compute it. Our model, in principle, tells us the probability of the data, or our prior odd parameters together with our model in principle tells us the probability of the data, but computationally it's often very difficult. You might have to do a sum over 2 to the million different possible outcomes. However, you don't usually get to do this, but in this case, we can completely ignore this term that's hard to compute. And the reason we can is that we're concerned chiefly about which parameters are more likely than others. And this term doesn't depend on the parameters. And so we can, when we're comparing the relative probability of two sets of parameters, we can just plain ignore the probability of the data. All right. And so what that gets us is that the probability of parameters given data, the posterior, is proportional to the likelihood times the prior, the data given parameters and the probability of the parameters. And this is a really important equation in machine learning. It's basically how do you update your belief about your parameters given evidence. All right, so let's go back to our coin flip example. So, or more generally, the example where we have a bunch of IID data. So let's write X for all of our data, meaning N IID repetitions Xi, and theta is our parameter. Our data set is a random variable, which means, we can consider conditioning on it as we have been doing. Our parameter could be just a single number like the probability in the coin flip, or it could be a vector of numbers. It could be like the weights of a linear classifier, for example. And so with this notation, Bayes' rule says probability of parameters given data is proportional to the probability of parameters times the likelihood probability of data given parameters. So you'll see this form of Bayes' rule often, and you'll also see this form, which uses the IID assumption. By conditional independence, P of x given theta is the product of all P of xi's given theta. All right, so if we now go back to our coin flip conclusion, so the probability of xi given theta is going to be very simple, right? So theta is the probability of turning up heads, which we're going to write as xi equals 1. And so the probability of heads, that's by definition p, if we saw heads. And then the probability of the data is if x is 0, meaning if we saw tails, is just 1 minus the probability of heads, right? And so if we collect that together in this equation, right, the product of all of the P of xi's given theta is just going to be theta to the 15 for the 15 heads times 1 minus theta to the 5 for the 5 tails, right? And then if we assume a uniform prior, that drops out, and we get that our posterior looks like this. And so before seeing our data, our prior would have been a uniform distribution over this entire interval, and now after seeing the data, it's this this curve here, right? And so what I've done is just sorted all of the possible values of theta and plotted the height proportional to the probability. And so you can see so a couple more questions. Let me just look at that. So there's the question of whether TensorFlow uses Taylor series approximations for automatic differentiation. Um, so implicitly, every time you're differentiating, you're building Taylor series. And so I would say implicitly, yes. Right, you're effectively, I mean, TensorFlow is effectively going to be using the same tools that we've been teaching over the past few weeks, these matrix differentials that implicitly represent Taylor approximations. TensorFlow is going to be using those inside. Of course, there's a lot more to it than that, right? You have to decide, given a complicated expression, what's the best way to break it into pieces and what to differentiate first and all of that. So, there's a lot more going on, but yeah, basically the derivatives represent that. All right. So going back now to, this is our posterior, right? And so if you look at it, all of the most likely values for the probability of heads wind up being above 0.5, right? So our original question is, was the coin biased? And the answer is probably, right? Like all of the ones above 0.5 are much more likely than all of the ones below 0.5. We can actually put a number to that and ask what is the probability that the coin flip parameter goes in some interval here. So if we take the interval from 1/2 to 1, it's almost 99% likely that that the value of the parameter is in that interval. According to our posterior. Or if we ask, like, what's the probability that it's greater than, let's say, about 0.7, right? And that's going to be, it looks like more than 1/2 of the probability is going to be greater than 0.7. And so, if you had to bet, yes, the coin is likely biased. But it's not 100% sure, right? There's some possibility we just got, a great run of luck, that we should have played the lottery today, and that it's actually 0.4, right? That's a probability that's actually noticeably greater than 0. Right? The probability that the heads probability is 0.4 is noticeably greater than 0. So that's a plausible outcome. All right. So instead of reporting the entire posterior, it is useful often to report a summary of the posterior. One common summary is just to pick an interval, and say, like we just did, and say what's the probability that you're in that interval. You could, for example, pick the highest probability, right, the shortest interval that you can to get a given probability, and say, for example, from about 0.6 to about 0.9, right, contains a good chunk of the probability. So if you don't want to report even an interval, if you just want to report a single number, the most common thing to do is to look for the peak of the posterior probability curve and just report the value at that peak. And the easiest way to do that is going to be to go back from a discrete representation to a continuous representation, so that now we have, in this expression, we consider theta to be a continuous number. We differentiate with respect to theta, set the derivative to 0, and find the maximum. Right? Should point out that the thing about uniform versus non-uniform discretizations, you have to account for that when you're using this trick of going back to a continuous representation, but you can do that, or you can just start with an even discretization to begin with, and then that works. All right, so in our example, it's pretty easy to do, right? So what we're going to do is maximize the log of p of theta instead of p of theta itself. So 2 questions: why does that make sense? Why is it valid? And second, why is it a good idea? So first, why is it valid? If you're maximizing p of theta given x, you can equivalently maximize any monotone function of p of theta given x, because if theta 1 is higher probability than theta 2, then theta 1 also has higher log probability than theta 2. So that's why it makes sense. Why it's a good idea, we'll see in a second. So let's just try it, and we get something that looks like this, right? So if we go back up and get p of theta, right? P of theta given x is theta to the 15 times 1 minus theta to the 5. If we take log of that, we get 15 log theta plus 5 log 1 minus theta. That's this here. And then we should acknowledge the fact that there's a normalizing constant which we haven't computed. And when we differentiate, right, the constant goes away, and we get d of 15 log theta plus 5 log 1 minus theta, and so that's 15 d theta over theta, because the derivative of log theta is 1 over theta, minus 5 d theta over 1 minus theta. You get the negative because of the negative in front of theta in that expression. And if you solve that, right, if you set that equal to 0, again, the only way for this to be 0 for all d theta is if the coefficient of d theta is 0. And so you get that then you multiply through by theta and by 1 minus theta, and you get 5 theta is equal to 15 times 1 minus theta, or theta is 15 over 20, or 0.75, right? And so this is maybe unsurprising, but it's good that, you know, after we work through all the math, we get an answer that makes sense. The reason it makes sense is that 3/4 of the time in our experience, the coin has come up heads, and so the most likely value for the probability of heads is 3/4. And so now going back, why did taking the log make things easier? It's because when we differentiated this expression, we got to use the sum rule, right? It was a product of a whole bunch of terms, so when we took the log, it became a sum of a whole bunch of terms, and we got to use the sum rule. And the sum rule is easier to work with than the product rule, because the product rule keeps doubling the number of terms we've got. All right. So, oops, there's another question here. Oh, right. So somebody asks if it matters whether you split your data, right? So you consider it as one data set of 20 coin flips, or as 2 consecutive data sets, one with 11 coin flips and one with 9 coin flips. And the answer is no, right? If you condition on everything all at once, or you condition on the first 11 flips and then the next 9 flips, you'll get the same answer for the posterior, at least as long as you do the math right. That's a good question. Now, there are a lot of approximations that people will make that might not be invariant to that, and so you can still watch out for that. But even I think most of the approximations will wind up being okay. The one main example would be optimization. So if you reach a local optimum when you're trying to find the maximum likelihood or the maximum a posteriori point, you might reach a different local optimum if you optimize first over half of your data and second over the other half. All right, so I said we had to pick a prior. And if we pick a different prior, we'll get a different posterior, and therefore we'll get a different map estimate. And that's potentially a problem. And there can be some pretty extreme cases of this, right? So if we're talking about a coin flip and your prior says that the coin probability is uniform between 0.2 and 0.4, and mine says that it's uniform between 0 and 1, you're never going to get 0.75 because your prior assigned it 0 probability. So you'll get 0.4 as the most likely answer, and I'll get 0.75 as the most likely answer. So it makes sense to try and come up with a single answer, a single estimate of theta that everybody can agree on. And the closest thing that we've got to that is what's called the maximum likelihood answer, which is basically maximum a posteriori, where we fix the prior to be uniform. And that makes sense in some sense because a uniform prior is maybe the least informative possible choice, meaning the choice that assumes the least information before you see your data. And so it seems like a good compromise because, you know, you're not forcing your own prior onto somebody else, and they're not forcing their own prior onto you. And in the coin flip example, we already used a uniform prior, and so our map estimate was in fact a maximum likelihood estimate. Now, let's get back to the meaning of a uniform distribution and this problem with this discretization. If we discretize differently, we're still going to get a different answer, right? Uniform distribution over C-style floats is different than the uniform distribution over fixed point numbers, meaning an even discretization of an interval. And so we haven't gotten rid of all arguments, we've just pushed them from an argument over the prior to an argument over how we discretize our parameter space. Or in the continuous case, there's a similar argument, which is what transform of the parameters do we work with? For example, do we work with the parameter itself or the log of it? Which one makes more sense? And again, there's no good answer to this. But there's one saving grace, which is that the more data we have, the less this issue matters. The maximum likelihood estimate, meaning the map estimate with a uniform prior over your entire range of parameters, that maximum likelihood estimate converges as you get more data. And so no matter what prior you started with, no matter what prior you started with, as long as it gives positive probability to every value of theta, you're going to wind up getting the same limit, or the same limit up to the accuracy of your discretization. All right. Somebody's asking, where is P of theta in this expression? In this expression here, P of theta has gone away because of assuming a uniform prior, right? So P of theta is constant with respect to theta, and so I just got to drop it. So that's a good question. I didn't adequately emphasize that that went away. So so there's a question about this expression, right? How it maps to this expression, right? So each one of these thetas maps to one of the P of xi given theta, right? And in particular, they map to the i's where we got the heads, right? Each one of these 1 minus thetas also maps to one of the P of xi's given theta. And in particular, they correspond to the i's where we got tails. And then this P of theta, this maps to just 1 because we're assuming a uniform prior. And so that's how we get this expression here. All right. So we got through maximum likelihood, and we pointed out that you can't get away from the problem of, do you maximize with respect to theta or log theta, or do you discretize, with a float or with an even fixed point discretization? But that in the end, if you have enough data, it's going to hopefully silence all of the arguments. So I wanted to just now go back and summarize, and as we summarize, talk about the common mistakes that people make with this, because it is extremely useful, but sometimes subtle, and so extremely useful things get used a lot, and subtle things often have mistakes in them. And so I wanted to point out a few of the most common mistakes to watch out for. All right, so the procedure is basically we start by designing a model that captures all of the behaviors that we want to reason about for the data. For example, all of the values of the probability of heads. And that model will have a parameter vector, which we'll call theta, and that represents the information we want to discover. After we've given that model, we assign a prior to all of the possible values of our parameter vector based on the knowledge that we have before seeing the data. If we want to minimize the effect of the prior, we choose a uniform prior over a wide range of values of theta. If we don't want to minimize the effect of the prior but actually have some useful information coming in, then we encode that in the prior. Then we observe the data and we use it to compute the unnormalized posterior by this application of Bayes' rule. And then once we've done that, we can normalize the posterior, which might be computationally difficult, but we can try to do it, and report the probability that theta is in some event E, some set of interesting values of theta, like a confidence interval, for example. Or we maximize over theta and report the best value of theta. And we call that either the map or the maximum likelihood estimate, depending on whether we used a uniform prior or a prior that was intended to be more informative. Right, the maximum likelihood is with the uniform prior. All right, so what are the mistakes that people make? Maybe the most common mistake, and it's a mistake that we even make intentionally some of the time, meaning that we don't have a way around it, and so we just deal with the inaccuracy. The first mistake is to assume too simple a model class. The posterior being reasonable depends on our model class and prior being reasonable. And often for computational reasons, we choose a model class that's too simple. And so you'll see in papers something that says, with probability 99.997%, the following conclusion is true. When what they really should say is, assuming that all of our modeling assumptions and prior distribution are right, which we actually know that they are not, then we get the 99.997%. And very few papers, put that rather important caveat with their results. And so if your modeling assumptions are very wrong, you're going to get complete garbage out of your model. Maybe more insidiously, if your model assumptions are just somewhat wrong, you can get somewhat wrong conclusions that still look plausible. And so there have been many, many papers published where somebody advocated for a conclusion that later turned out to be wrong when they used a more sophisticated model to analyze their data. All right, the second mistake people often make is to pick a sample that isn't representative of the population that they want to reason about. Right? So, for example, if I stand, on the corner of Forbes and Craig over that way, and do a survey and ask passersby if they know about anonymous functions, and let's say 30% of passersby say yes, I use them all the time. You might be tempted to conclude that 30% of people in general know about anonymous functions, but you would be wrong because your sample at the corner of Forbes and Craig is not representative. Right? You get a whole bunch of CMU students walking by, and they're more likely by far than the average person to know or care what an anonymous function is. All right, another common mistake is overfitting. So you've probably all seen examples of this. If you try and fit a really complicated model with not enough data, then you get useless answers. And at a high level, the problem is that you shouldn't expect to get a lot of information out, meaning accurate values for lots of model parameters, when we put very little information in, meaning not very much data. There are ways to try and guard against overfitting, and that's a lot of what people talk about in machine learning classes farther along in the sequence, but for now, just watch out for it. The last one, which is actually, it's a special case of overfitting, but it's one that people don't often realize, is what's called the multiple test fallacy. And that is if we try and fit a lot of different models to our data and pick the best one, just by chance one of the models might turn out to work well. And if we fit enough models, it's highly likely that just by chance one of them will turn out to work well. If you haven't seen the XKCD that's linked from the lecture notes, I encourage you to click over. But in general, there's the what I like to call the NIPS deadline problem, right? Which is that a week before the NIPS deadline, you start fitting 100 different versions of your model to the data, one after the other, in hopes that you're going to get a nice looking result, which you can then paste into your NIPS paper and hit submit, 2 minutes before the deadline. So it's really tempting, right, to do multiple tests. And there are corrections you can do so that you actually can do exploration, try different models. But if you don't do these corrections, you will get bad answers. All right, so, oh, somebody would like an example of overfitting. Yeah, so I'm trying to figure out what the best way is. They're asking for a visualization. I don't know if it's easy to visualize because it typically happens in high dimensional spaces. But think about it like this. Suppose you are looking for genetic differences among people that are associated with some condition like, let's say, cancer. So people actually do this. What they'll do is they'll go and they'll sequence the genomes of 1,000 people, which is surprisingly inexpensive these days. And then they'll go through and they'll look at genetic variation in those people, and then they'll follow the people for a while and see which ones get the illness in question. And there are, I forget how many, like there's billions of base pairs in our genome, if I remember right. And so, we don't actually, typically people will measure on the order of thousands or tens of thousands of these variations. And so if you look through them and there's let's say just a few more people who get a slightly higher proportion of people who get the disease when they have some gene variant than if they don't. If that were the only gene variant you were testing, right, it wouldn't have to be a very big difference before you were confident that that was actually something that you something that was a real result. Whereas if you if you look over all 10,000 gene variants, just by random chance, some of them are likely to have more people who get the disease, and some of them will have less, right? Because it's a random process. It's good or bad luck for whether you get the disease. And so, just by chance, some of them are going to seem to have a little bit more association with the disease, and if you don't correct for that, you're going to almost certainly find some results that aren't real. Right? Another question would be, another way of thinking about it is, suppose that you wanted to figure out the height of the tallest person in our class, right? But you instead found the height, suppose you wanted to figure out the height of the average person in our class, but instead you figured out the height of the tallest person, right? That would be not a great estimate of the height of the average person. And so, that would be a bad idea. And so in the genetic testing example, what you're doing is you're trying to find out the association of the most associated gene variant, and that's like searching for the tallest person in the class. All right. So that I think is the end of the material that I want to talk about for the mini. Hope everybody's enjoyed learning about it as much as I've enjoyed teaching about it. We have 20 minutes left in the class period, so I'm just going to watch Piazza and if you want to ask general questions or questions about any topic that we've seen, I think it makes sense to spend some time in class answering those. So the first question is whether I can give a summary of topics for the exam. Yes and no. I can give a summary. It may not be a summary that the poster will like. The summary is please click on the syllabus for Mini 1 post, which is pinned to the top of everybody's feed. So logic and sets, probability, linear algebra, functions and function spaces, matrix calculus, matrix differentials, and then today, of course, statistics and inference. That's the themes or topics. I would say maybe a slightly more helpful answer is what we want to emphasize throughout the whole semester, not just the exam, is using these concepts to solve problems that are of a form similar to what you would see in 601. Again, we'll pick instances that are maybe simpler than what you would have to solve in a 601 homework, but we're going to try and pick things that have a similar flavor. Somebody is curious about how you would go about correcting in the gene example. That is a subject of much debate, actually. What you wind up doing is basically there's a formula that allows you to correct your degree of belief in a conclusion based on how many different tests you made, out of which this was the largest result. So two names that go with that. One of them is the Bonferroni correction. I'll just Bonferroni correction. Right. So if you just look at Wikipedia at the Bonferroni correction, that's one. The other common one that people use, maybe even more commonly in the gene example, is the false discovery rate correction. And again, it looks like there's a Wikipedia page on the false discovery rate. And people will also people will use that fairly often in a paper about, this is called a genome-wide association study, when you go trolling for gene variants that are associated with a condition. And that's probably, the false discovery rate is probably the most common correction people will use in a paper like that. Oh, somebody's asking about the exact timing of the exam. You know what? So I was let's go ahead and say yes. What we'll plan to do is we'll release the exam at the beginning of the class period. Everybody should plan on taking at least the class period to work on it. It's going to be written so that you should be able to finish it within that class period. But we're not going to ask you to hand in all of the electronic parts until 11:59 p.m. that same day. And that gives... the nice thing about that is that it gives like extra time in case something goes wrong in scanning and uploading a PDF, or extra time in case there's some really inscrutable bug that you can't find in some small programming question. Now, the goal is not to have everybody like, spending their entire evening working on our exam. That's not what we want. And it's also not to have everybody trying to upload the exam at 11:58 p.m., right? So we're not going to accept late submissions for the exam. So make sure that you upload early, upload often. Do not leave the uploading at to the last minute. All right. So I think I don't see any more questions right now on Piazza. I think what I'll do is I'll just pause the stream for another few minutes and wait and see if there are more questions. And if so, I'll come back and answer them. So I'll see you back in a few minutes. Hey all, there's a question about geometry of drawing a line in a plane. That seems like a good thing to use the lecture stream for. So let's go about doing that. So what does that look like? So we have a vector. So the line is going to be we'll have parameters w and b, and the line will be the set x such that w dot x plus b equals 0, right? Or we might actually, sometimes we parameterize it as w dot x equals b, right? That's just a question of the sign of b, so just make sure which one is the convention that we're using. Right now I'll scratch that out because we'll just fix this convention here that's on the that's in this equation. So the first thing to do, right, is we'll draw a set of axes. And then we draw our vector w, right? So let's suppose that w is 2, 1, right? And so so we draw the axes in w, and then the first thing to note is that w is going to be the normal vector to the line, right? So our line is going to look like that, or like that, or like that, right? So the easiest thing to do is to solve for the places that the line crosses the axes, right? So let's say, for example, so the way we do that, right, is look at look at something like w dot 1, 0 plus b equals 0, right? And so here in this case, w dot 1, 0 is 2, and so b has to be equal to -2, right? And so if, sorry, what I just did was I solved for what would b have to be if we knew that it crossed at 1, 0. What we would typically want to do is go the other way around. So we'll write a point on the x-axis as w dot x1, 0, right? And so that is going to say 2x1 plus b is equal to 0. And so let's say, for example, that if b, oh, whoops, that's going to be under my picture, isn't it? Let's scroll up a bit. Let's say if b equals -2, then x1 would have to equal 1 in order for that equation to hold, right? And so what that would mean, let's say that this here is the point 1, 0, right? And that would correspond to b equals -2, right? Whereas let's suppose that let's suppose instead if b equals -8, right? Then 2x1 equals 8, x1 is equal to 1/4, right? So this here would correspond to 1/4, 0, and it would correspond to b equals -8, right? Whereas over here, this line might correspond to an intersection of -1, 0, right, which would correspond to a value of b equals +2, right? And so just scrolling back up again, basically what we do is we start by drawing the axes and the normal vector, and then given our particular value of b, we figure out one or the other of the intercepts, or possibly both of them, and we use that to decide how far along W to go to draw our line. Hopefully that's helpful. Somebody's asking for a reference on matrix differentials. I can post, there's a nice tutorial by Tom Minka. It's at a maybe fairly high level, but it's a nice reference. There's also there's this book, which I'll post the reference to. It is, again, like, it's kind of thick, so I don't necessarily recommend reading the whole thing, but it's very useful. It's the one that I learned matrix differentials from in saddening detail long ago. All right, so I think now is probably a good time to stop. My office hours start now, so feel free to keep asking questions on Piazza and/or come give me a visit. And good luck with studying for the exam. And we will see you guys virtually in class on Monday. Thanks.